Here we have a couple basic torque examples. In this first one, there's a boy on a seesaw, and on the other side of the seesaw are some cement blocks or bricks to balance his weight. Now, in this particular example, pivot happens to be right in the middle. It's very important you identify the pivot before you start a problem, because you're going to measure all your distances to that pivot point. Now the blocks on the left side have a weight of 100 newtons. We're going to label that F1. They are located a distance of 2 meters from the pivot point. We're going to call that L1. The boy, his weight's not known. The distance from the pivot point for the boy, though, is going to be 1 meter. That's L2. Now, the key for balancing a seesaw is to use torque. Now, if you remember, the basic formula for torque is just the perpendicular force times the lever arm. This works whenever the forces are at 90 degrees to the seesaw, which is the basic case we have here. If there's angles, you just go back to use the version we talked about. That's FD sine theta. But for us, F perpendicular times L is going to work just fine. Now, how you approach this is each one of those forces that are a distance away from the pivot, they're going to create a torque. F1 is going to create a torque that would want the seesaw to rotate in the counterclockwise direction. We'll label that tau 1. The boy on the right-hand side, the force pulling down, would create a torque that would go clockwise. We'll label that tau 2. Now, in order for the seesaw to be balanced, or to be in static equilibrium, those torques need to be balanced. They're the only torques present. One goes clockwise, one goes counterclockwise. We'd write that as tau 1 equals tau 2. Filling in the formula for torque, it's simply F1L1 is equal to F2L2. Putting the numbers in, you see that 100 times 2 has to equal the unknown force times 1. And that works out pretty easily to be that the unknown weight of the boy is 200 newtons. Now in this next example, it's just a little more complicated. The boy's on the right with 2 sets of bricks on the left. Okay, again, pivot's right in the middle. Now the first set of bricks, it's the same 2 bricks we had before. F1's 100 newtons, but it's moved in closer. Now the lever arm for those bricks is just 1.25 meters. The second pile of bricks, 150 newtons. The distance, I'm not going to tell you exactly how far it is. We're going to figure that out. Now the boy on the other side, well, we just found his weight to be 200, and he stayed put at 1 meter away. Again, basic formula for torque will work. Just take a look through at all the forces. F1 will create a counterclockwise torque tau 1. F2, the second pile of bricks, also creates a counterclockwise torque. And the boy on the right creates the only clockwise torque. So to be balanced, all the clockwise torques have to equal all the counterclockwise torques. I'll write the counterclockwise first, tau 1 and tau 2, added up have to equal tau 3. Throwing in the formula F and L, looks like that. Putting the numbers in, you can see that 100 times the 1.25 plus the 150 newtons times whatever its distance is has to equal 200 times the distance of 1. Doing the algebra, you can see this come together so that eventually L2 works out to be 0.5 meters.